Okay, welcome everyone to this week's online causal inference seminar. This week we have Ricardo Silva from UCL giving us a talk on intervention generalization, a view from factor graph models. Our discussant today is Anish Agarwal from Columbia University. The Q&A will be handled by Emma today, and Emma will let you explain the rules.
Thanks, Jialin. So yes, please submit your questions throughout the talk. Please use the Q&A form at the bottom of your screen to submit it, and not the chat. We'll moderate, we'll kind of watch them rolling in, and when Ricardo makes a pause, we'll ask your questions. This is an old format seminar, so please feel free to just keep submitting your questions throughout. And yeah, hope you enjoy. Okay, Ricardo, I think you can start sharing.
All right, you can see it, right?
Yes, we can see it.
Yeah, looks good.
Okay, so let's start. Thank you very much for the introduction, for the invitation. This is joint work of a few collaborators of mine from UCL and King's College. So I'm going to introduce what I'm about to talk by an example. This is a well-known example by some people that work in graphical models, where we have a systems biology problem. There are some concentrations of proteins and lipids that are measured at cell level. They have all sorts of perturbations to the metabolism of that cell. So it could have some inhibitors or some other sort of stimuli that is added to the cells, so the behavior of the cell will change. So here's a kind of high-level diagram showing some of these little green circles indicating types of perturbations, and the red ones are the types of inhibitors. You want to know what will happen to the concentration of these elements in the cell when those perturbations take place. But in principle, you have maybe large combinatorial spaces of possible perturbations. You may ask yourself, given that some combinations might not be in that data, what will happen if I actually want to perform them? This could in principle be done if you just fit a sort of model that maps the perturbation status of past actions to particular outcomes of interest. But this space may be very large. You may not have any sort of good smoothness assumption that would link particular combinations or permutations in that data to unseen combinations that you have not done before. And one extreme example is when you have observational data that you do no perturbations at all. You may want to ask what would happen if there were to perturb the cell in a particular way. Then in this case, you don't have basically any other variation in possible perturbations to rely on to be able to make such a prediction. So how to tackle this problem in a systematic way is what I'm about to present. But I'm trying to cover here not a sort of completely all singing, all dancing solution, but to focus on particular types of generative processes and what you can do in those cases. For the generative processes I'm interested in, are related to this type of data set in cell biology that may be rich in feedback loops. So people can try to learn, for example, some sort of causal structure relating to these measurements. Often they fit acyclic models, and they may not be very representative of what is going on, because you may have some sort of feedback between the different parts of the cell. Also, if you want to try to model dynamics, you'll also be unlucky, because in many cases, when you try to measure something like a cell, if you do that once, you destroy it. So you're not able to really sample a path of any particular individual cell a long time when you have one shot to measure things. And the perturbations themselves are not your textbook clean interventions that you may have in theory. They're actually complex biological processes, right? This is a table taken directly from that paper, which tries to provide a bit more of a level of detail of what is going on when you say they're perturbing a particular protein concentration. We have all sorts of inhibitions, for example, in different components of the cell that amount to a particular intervention, which may actually affect several things at the same time. And as a matter of fact, people have tried to put these ideas to test. So there are some papers like this old paper by Ethan Murphy, where they did not assume they knew the target of the interventions. They tried to learn which possible perturbations were linked with type of measurements in their cell. And the outcome was a very dense graph, as you can see here, where these red nodes denote some sort of perturbation indicator, whether you're leaving it at rest or whether you're actually adding the perturbation. If you just let a data-driven approach find these links, we're going to have a very dense set of connections showing that perturbations actually may shake up several variables at the same time. So what we're going to do here, we do assume that we have all sorts of data sets with different combinations of interventions. We are going to represent just as a plain vector signal here that encodes which type of perturbation you're doing. So given this vector signal, we want to know, well, what will happen to the measurements that I actually make after adding these perturbations. The data you have are basically single snapshots of a possible stochastic process. You don't measure trajectories, measure a single snapshot, maybe under equilibrium, maybe at a particular agreed upon time in the process. There are feedback loops galore, and your interventions cannot be assumed to just target particular variables, or change several things at the same time. And while we have had a bird's eye view, what we may have is you have a representation of the intervention vector. There are ways of encoding this perturbation is done or this other perturbation is done. Let the clock run, you do some sort of measurement of your cross-sectional behavior of the cell. Destroy it, that's it. There's no more pathway to be measured here. You may wait on a particular time point. You may wait long enough to be able to declare, well, this is equilibrium. From that point, it is a stationary distribution. But whatever it is, I'm assuming that you know what you're doing. And while we're trying to do that, maybe it's not the classical directed graph models that you see a lot in the literature. Let's try to understand that underneath the measurement you're doing, you have to wait for some sort of process to take place. So this is a kind of classical paper by Sternlowitz and Thomas Richardson, where they imagine there's a sort of Markov chain behavior. We have your random variables where each random variable at a particular time is sampled based on the status at the previous time point under particular interventions that you here represent what is AB. By the end of the day, you measure what happens in the end. And this can happen in social sciences too. This is other example by Elizabeth O'Byrne and Yoshi Pizza, where you have a social network, you use some particular information, let's say, to people in a social network. They may know each other and gossip to time about how this information is being acquired or understood and talked about people in a social network. And by the end of the day, we have a single interview process asking people what they know about a particular thing or how they behave under a particular stimuli. So all these processes get hit, and we want to say, well, there is some sort of connection at the level of the cross-sectional sample I took, but this connection may be confounded in all sorts of ways because of the hidden process you did not measure. So may want to understand that there is some sort of approximate structure of independence that you still rely on. So if you think that we need to have some sort of social connectivity for information to propagate, we want to say that whatever stimuli give at the beginning will propagate only via these physical or social connections that you have in the system. It's the type of information that you see here that will allow you to kind of create a piecewise representation of how this entire initial shock or perturbation will propagate and indicate what the state of the system will be eventually. And sometimes this also shows up as ways or problems related to mediation. So one often formulated questions such as, what is the effect of a treatment via a particular pathway? And sometimes you interpret this as two versions of a treatment being set to a pathway or set to another pathway. So an example like this here, which is a made-up example, but may be interesting as an illustration, may have the effect of cigarette consumption on cancer. We want to understand what it means if it goes indirectly via deposits of tiny lungs. And one reason why we wanted to know that is what if you were able to try to decouple the effect of nicotine in a cigarette from everything else, assuming that nicotine operates mechanistically only via this pathway of timelines. Now, there are approaches for that based on nested counterfactuals and principal structure, how people respond to particular exposures. They can be contentions in the sense that they do have this crossword flavor, taking counterfactuals that cannot be resolved at the same time. But another way of understanding this is if you think about components of a treatment, maybe you wanted to know whether you can explicitly separate them. So you'd be able to say whether a cigarette has nicotine components and other components. Maybe you can envision a sort of treatment where just a nicotine component of it is deactivated. So you could have here a contrast such as this that you'd like to know what will happen to a person if I cannot deactivate this mechanism via the possible timelines. So if this means a treatment that has structure, may say that you try to contrast what will happen to the individual when you flip one of the entries from one status to another status. And this has linked this idea of finding effects of combinations, because in your data, what you may have is just smokers and non-smokers. In this case, don't consume any part of a cigarette or consume all parts of a cigarette. But you want to query this type of combination that has not been in your data. The structure may help you with that. In a model like this, we would have, under the assumptions of this model, that the component of nicotine affects the outcome only via this deposit of timelines. So to be able to learn from the data you have this particular effect of the system, and also this particular effect of the system for any combinations of A1 and A2, assuming a positive distribution, and be able to reconstruct this particular scenario of interest. You can see that in the literature is motivating some sort of non-counterfactual, purely interventional definitions of mediation. Okay, so what are we going to do next based on these ideas of understanding what you're actually measuring as a snapshot and how decomposing an action may be relevant to understanding new combinations. I'm going to describe ways of just putting them together in a relatively simple graphical model that includes intervention indicators explicitly on it. And the bulk of the technical part of the talk is really talking about how you identify, or you can be able to say whether you can identify combinations of interest, even those that are already in our data. So let's start by what I'll be assuming on the data before I describe which type of models we'll be able to make use of them. But the assumption, as I said, have a collection of data sets, little t data sets here. Each one is generated on a particular regime. The way I'm describing the regime is just a vector taking categorical values as its entries. So any particular entry here will come out of here of an encoded natural number describing which type of treatment level you have. So you could have 0, for example, indicating a kind of observational regime. The data set will have IID samples of some vectors X and Y under each of these regimes. Y may be some sort of L entry of X that you're particularly interested in, but in general may be interested in the systems as a whole, the whole vector X. And given a set of data sets which you know which regime they have been collected on, may have a new regime we're interested in, where you may want to notice the behavior of the entire system, or just one particular variable, a summary of its distribution, like the expected value. This is a setup that appears in all sorts of other papers too, including, for example, approaches to understand what happens when your interventions may not be necessarily exact, but only stochastic. So in terms of assumptions of our model, we know a factorization or the density in a way that I'll describe shortly. It will correspond to some sort of canonical graphical model that will, in one sense, facilitate knowledge elicitation or structural learning for obtaining it. And I'll describe after that how would you be able to say whether from the training regimens you have, whether you'll be able to piece together information to infer what will happen on the new scenario sigma star. So I will start by adopting a very standard family of multivariate distributions that take this shape that's sometimes known as energy-based modeling. So the idea here is, again, should be familiar to many of you because it's one of the oldest ways of creating multivariate distributions is inspired by statistical mechanics. Here, joint distribution is defined by just renormalizing some sort of exponentiated inner energy function. So the idea here is that low values for this function will correspond to high probability states. And depending on the shape of this energy function, have kind of a notion of modularity. Not the type of modularity you see in things like directed graphs, but a type of modularity that nevertheless can be used to carry out causal modeling if you explicitly represent how these random values interact with actions. So the actual vectors here will have meaningful physical interpretations that are domain dependent, may, as I say, encode the level of 0 as just as a default state with no perturbation. You could in principle encode it in terms of the more canonical atomic interventions that is in the causal inference literature, where there is maybe one particular value xi that is set precisely to a particular value. But in general, they don't need to be this sort of very precise interventions. The perturbations of many kinds, you throw an inhibitor in the middle of the cell. And this inhibitor doesn't need to have an exact correspondence with a single random value. It could affect a set of values at the same time. Now, we'll need to somehow understand the dependency structure between these interventions and the random variables. You will have to understand or extend the notion of conditional independence to the use to this regime indicators because they are not random variables. They're just a kind of switch saying one particular regime or another. There are very formal ways of carrying this out, but for the sake of this talk, you can understand that if you say whether a particular intervention, a particular random value are independent, all you're saying is this random value is equal in distribution on a different levels of this intervention variable. So let's see this motivated with a highly simplified problem. So this problem here, as you imagine, is again motivated by a dynamic system that reaches an equilibrium. In this case, we have a kind of bath where fluids are getting in and some fluids are getting out. There's a depth of the bath and there's a pressure at the bottom of it. You could ask some mechanistic modeler to write a set of differential equations on how these different measurements are varying over time. The depth is varying over time according to pressure. There's the rate of change by pressure. And at equilibrium, all these rates of change will be zeros, and those define particular constraints on these random variables. Now, in a system like this, it's very mechanical and principle. Maybe you could control some of these variables. Right? Maybe you could control the gap in this flow here to see what was the ratio by which liquids are invading the pool. But in practice, there are all sorts of problems that real data will pose to you. To begin with, even observe dynamics in a system like a cell biology application, be very hard to have much confidence in the differential equations that you're writing. And also, the interventions we have, as I said, they're not exactly controlling a random variables directly. So from a pragmatic point of view, this would motivate defining which sets of variables will be tied by constraints. The parametric shape of the constraints will be unknown, but they will be modified by interventions again in a way that you may need to learn from data. Now, these may be very loaded in terms of assumptions, but in principle, everything is formulated in a way that you could test by experimentation. So even if you observe only a partial set of experiments, they will have falsifiable implications in terms of which interventions are interacting with which random variables. The energy function here is kind of interpreted as describing that the more you violate these constraints, the lower the probability of the system, your system state would be. And everything here is predicated that you have agreed upon what the time of the cross-section set you're doing is. Because if you have a non-stationary behavior after perturbation, of course, at each stage in time, we have a different distribution. It may be a different set of qualitative constraints. So you have to agree upon exactly which period in time you'll be measuring your variables. So, given that we have this classical way of describing multivariate distributions, what is the role of a causal intervention? You could derive classical causal DAGs with explicit regime indicators here denoted these square vertices, saying that each one is variously modified according to this particular interventional parent. So its condition distribution modified based upon that. One way of understanding this in terms of energy base mode is to say, well, what the end of the day is that just factors that depends on subsets of variables and subsets of intervention variables. So in the literature graphical model, you already have a language for that called a factor graph model, where you indicate the interactions that you have. So if you have X3 having a condition distribution between X1, X2, and sigma 3, that condition distribution can be qualitatively described as an interaction between all variables, all random variables here, and this intervention variable sigma 3. So these factors here correspond to the factors of a DAG. This is just a way of describing an example, because to describe a set of factors like this, you don't need to start from a DAG, but start from some sort of rough set of differential equations you think would hold in your system, and from there derive which factors and interactions you have. If these factors are not just describing condition dependence constraints, they're also describing particular sorts of interactions you may or may not have. Because if you were to write down a more classical graphical model describing the Markov blanket of these variables, well, this variable x1 will be connected to everything given by conditioning the other remaining random variables, right? You look at the system that you have here, you condition x2, condition x3, connect x1 to everything. So in principle, to have no indication in this graph that, as a matter of fact, there's no factor that includes sigma 1, 2, and 3 together, which would otherwise be read off from this graph. So there's not only independence constraints that we may be able to express with this type of factorization, but also these types of interaction constraints, here indicating that there's no factor containing all three intervention values at the same time. So a formula of this is very standard when you describe an energy-based model, just here explicitly indicating that each factor can switch to a different composition based on the status of these intervention variables. So the formulation identification problem here now can be described in terms of identifying densities that have this shape that includes the energy-based formulation. How this is compared against DAG formulations? I mean, this is, of course, very general approach in the DAG causal model literature. For example, the sigma calculus of Boy and Barenboim that come up with ways of solving this problem when you have DAG structures with intervention targeting a single variable. In a situation like this, the intervention doesn't need to be atomic. It can just be stochastically changing the distribution. But the DAG structure assumption is single variable connection usually assumed when we think about these problems of DAGs. However, the idea here is not really targeting a variable, right? As you saw in the initial example of the sectoral data, you're targeting what may be quite noisy, changing the relations among many variables. And this is known in the literature to under different guises. You can think of intervention changing not a particular variable, but changing, for instance, coefficients in a structure equation. This would be one particular way of understanding that the interpretation here is a changing relationship, not really a changing a particular variable. In this case here, you don't need necessarily the asymmetric considerations that we see in DAGs, where particular factors, if you marginalize the child variable, that factor disappears, right? There's no notion of child or parent having a factor when you think of just as a product of soft constraints. Now, given that you have this set up, you can describe a kind of set of identification results that complements what you have already in the DAG literature. I'll describe here via some examples. There's a companion paper for this talk. We'll go into the details in step by step, but here I'll just illustrate how we could possibly decide whether you have identifiability from the data that you have. So assume we have a baseline regime. This is just arbitrary. Here I'm just defining that the baseline regime is all intervention levels are set to 0 across a vector. I want to think about how to move from this baseline regime to the particular target regime you're interested in. So let's see this by an example. Suppose you have a graph like this, and you have the corresponding energy function described by these two factors that depend on signal 1, 2, or which depends on 2 and 3. In your data, you have all these 6 combinations of possible values of the intervention. Here's all binary. And the target distribution of interest is what if you switch all these interventions from 0 to 1. One starting point is, well, suppose I take this density ratio, right, where sigma 2 and sigma 3 are the same in both cases. So this factor of 2 would get canceled. Now, suppose I just multiply the numerator and denominator by the same factor. So again, just define the canceling out. But then I could rearrange them so that this numerator becomes the target distribution of interest, and the denominator becomes something else up to normalizing constant. So here, the ratio I started with is in the training set. The denominator I have here is in the training set. And the target I care is in the numerator here. So I'll be able to define how we'll be able to reconstruct this pink distribution here out in principle of distributions I could identify from my data. The idea behind this is to imagine a kind of decomposition of this graph where I could separate variables 1 and 3, and they have one in common, the variable 2. I could agree upon on the value of variable 2 here as the one that is required by a target distribution, and think about ratios that don't necessarily need to agree on the first variable because I can separate them in the factorization of the energy function. This is actually a type of message passing scheme where I'm able to decompose subsets of the factors in independent sets where I can just think about agreement on the intersection of these sets. This would have to assume some sort of decomposable structure of the graph that includes these regime indicators. But in principle, you'd be able to solve whether the identification problem holds globally for the entire system, but to which extent it also hold for particular subsets of that. This is a graph that is assembled by checking which regime indicators belong to a common factor. By looking at this graph and seeing there is some sort of separation, I could think of some problems I could partially solve without necessarily solve the entire problem, for instance. So even if you don't have global identification principle, you may be able to solve some partial identification for some subsets of combinations. Now, that type of approach is really aimed at some sort of decomposable structure, but in general, you can come up with solutions also that indicates whether a global problem is solvable or not solvable. And way of understanding that is get inspiration from this message passing approach that all you're doing there is taking products and ratios of densities that you do know. If you think about the space of possible products and ratios that you can do with the densities in your training set, can think about which ways I could do products and ratios to reconstruct a target density of interest. So here I'm going to explain this complicated table via an example again. In this example, the factorization doesn't have this nicely composable approach where I could solve things locally, independently and separately, and combine them together. Here, there's some sort of cycle between the signal variables, signal 1 connected to 2, 2 to 3, 1 to 3. Able to build a graph like this. You can have cycles among the signal variables, so we won't be able to apply this idea of message passing here. But instead, what I can think of is if you fix the value of the random variables to any particular constant little x, the factors that you have in this model can be interpreted as types of monomials on the space of the sigma variables. So what do I mean by that? So if they're all binary, for the sake of this example, you can think this factor here, for instance, is just a symbol which that takes different instances depends on the values of sigma 1, sigma 2. So if sigma 1 and 2 are binary, this would be one of possible 4 symbols depending on the state of sigma 1, sigma 2. Likewise, this could be thought again as symbols that index by sigma 2 and 3 and so on and so forth. Now, if you have a density like the density that will take place when all 3 interventions are switched to 1, this could be expressed up to a normalizing constant as a monomial on these symbols. In this case, the symbol where everything is set to 1. Now, this monomial needs to be reconstructed as products and ratios of the distributions which I have access to. One way of thinking about this is if you take the product of all distributions I have access to, we can raise them to a particular exponent representing whether I'm taking a product, in this key, if this is the exponent is 1, or ratio if it's -1, or what is ignored if it's 0. This particular example, I have in the training set 7 possible regimes, and that the density of interest is the one of all ones. In this case, I can think of the possible combinations indicating which symbols are included in the corresponding monomial. So the monomial for the distribution of signals are 0. This one corresponds to the product of these symbols. And each one of these, if I multiply them together, will correspond that some of these monomials have the corresponding exponents added up. So this monomial here for F1 appears in the first regime and the 5th regime. So the exponents Q1 plus Q5 will exponent of this symbol. This symbol doesn't show up on the target distribution, therefore Q1 plus Q5 needs to straight up to 0. So this defines a linear system. This linear system will have a solution or not. We can show it doesn't have a solution, so in general, it's not identifiable under products and ratios. But if it does have a solution, this will provide one way of reconstructing the corresponding target density by products of ratios on those densities, which in principle can learn from data. Okay. So I would like to say a bit more about how we do some sort of knowledge elicitation out that would provide a constructive procedure on how to create these models out of an expert of a structured learning algorithm. I realize I'm running a bit short on time, so instead of focus on that, which you can read through the slides here, which I hope are useful, I'm going to focus on the final part of the talk, which is just practical ways of fitting these models to data and how to link this to particular prediction problems. So one way of defining writing down likelihood function for this, or at least a way of estimating target densities of interest out of it, is to reduce the problem to, in some situations, to density ratio estimation, because under some particular graphical structures, we may be able to express the target density of interest as ratios of densities which you can estimate from data. So in principle, you could learn from data these density ratios directly and multiply them to rearrange our density of interest. I tried this and maybe to my own incompetence, it didn't work too well. But it's something that in theory could do reduce the problem to density ratio estimation problems. In practice, I found that fitting a likelihood function directly was more fruitful. And here, everything can be done very black boxy. You could think of the log factors in your energy function as being parameterized by a black box like a neural network. We had to take some care to avoid infinite normalizing constants, of course. In practice, I find that actually discretizing that data is not a bad idea. The number of parameters wouldn't change with the level of discretization because just treat the variables as real valued anyway. So this would guarantee a finite normalizing constant. And of course, you have the ancient problem of this partition function that is intractable, but there's now a lot out of there to fit these types of intractable problems by different criteria, different score functions. In experience, I've done a useful likelihood because it's on the simplest and better understood, but there's a whole literature on how to deal with these problems of fitting these possibly deep energy-based models, so to speak, with methods that avoid the computation of the normalizing constant. And one way of using this, as I mentioned, you could have a target variable of interest. And all you want to know is if I set up my design vector at a particular level, what will be the expected value of this outcome? It shows up a lot recently in machine learning literature on the guises such as causal bandits or causal Bayesian optimization, when we have a reward function of interest, a particular outcome of interest, and a subset of values which you can control. So you want to know how do I set up a level for these design values to maximize an expected reward. It's all embedded within a causal model. So the interventions you do in these manipulable variables are the things you can control. And the outcome will be a function that you get from marginalizing the structure between your control signal and the outcome. So this can be embedded if you wish to do so in a sort of active learning scheme where you try to minimize the number of interventions to be able to have, for instance, high expected reward. So one way of formulating this problem is simplified if you're able to say that your reward or outcome variable is conditionally independent of the design vector given that value is in your system, and ways of estimating the probability of solving the probability down to, among other things, estimating this expected outcome under a target intervention of interest. Now, given the shortness of time, all we want to do here is some sort of very brief summary of the experiments we've done in the companion paper. Please do look at the details there if you wish to get more details. But what we've done there, so test the sensitivity of this family of independence constraints you have compared to alternatives like a DAG-based model or a completely black box model. Because of course, what you could do is to have a design vector and have the outcome value. We can completely ignore any structure with the data that we have, just try to fit a model from the design vector to the outcome. This is doable under a variety of situations, but if you have a very sparse set of combinations in your training data, this will basically boil down at best a linear model. It depends which configurations you have available to you. Now, let me jump to an explanation of what this figure means here. So what I've done was the following. You have something like a subset of data set, which have only a limited number of combinations. So if you want to evaluate what happened on novel combinations, you'll need some sort of synthetic ground truth. So I fit a model to this data to generate a synthetic ground truth, which is based on real data at least. I fit a model that has a DAG structure that follows the original paper, and I fit a model that has this type of energy-based prioritization that is a relaxation of the DAG model in terms of independence constraints. So these are two ground truth models for which I sample training data. So I measure then some sort of root mean squared error in a test set of conditions that are not in the training set. And to see how they average over this set of conditions that are not that are novel, that test conditions. I have 100 synthetic Y variables. So the final outcome value Y is completely syntactic. I generate 100 scenarios and I make a box plot out of them. The root mean squared is normalized also by the scale of the outcome variable. So what's here at first sight looks a bit disappointing, that when the structure does come from a DAG, the DAG model does extremely well, and the black box model actually doesn't do too badly. Which here is an indication that my syntactic pipeline is actually almost linear in the intervention variables. This intervention factor model didn't do too well in this case, as you can see. They spread when it came from this ground truth. It's interesting to see what happens in the other scenario where the data does come from the stuff energy based model. In this case, as you expected, the model now starts to do much worse. But another thing to keep in mind here is, even though it looks like a win-lose scenario, when I plotted this, I tried to make things a bit more visually appealing, but the magnitude of the y-axis is very different here. These two, the behavior of this factor model in both cases is similar. If you look at the actual values of the y-axis, while the degree by which the two approaches are much worse, particularly of a much higher magnitude than the degree by which the factor model is here. So the factor model is slightly more stable in this sense, which is under a adversarial condition, may not do as well as other approaches. But when it's in a favorable condition, this alternative approach did much worse then. So there's a type of reassurance there that at least under a less optimal condition, would be actually not too bad in terms of absolute error. And could conclude, I'm still not very satisfied that the density ratio estimation applied here didn't quite work well. So I use the likelihood, but I think there's something to be said of exploiting better ways of applying density ratio estimation to this problem. And of course, everything is predicated on what we call a fantasy, right? That if you were to start a factorization, this factorization still be stable if you were to diverge a lot from the training regimes you have. I mean, even Newtonian mechanics breaks down if you just go close to the speed of light, right? So there's a limit where things will break down that extrapolate too far away from the training regimes you have, and which would be ways of diagnosing that when you're pushing things too hard. There's something to be said, of course, are ways of detecting whether a particular regime, even though it's identified, we shouldn't trust the results. You can, of course, compute density ratios and see whether they're too extreme. But maybe there are more smarter, more focused ways than that. And everything here was really based on this extreme scenario where you assume no smoothness at all between the design vector state to another design vector state. In practice, we want to if you have particular denser sets of training conditions, you may be able to also think through that some sort of smoothness conditions can be applied to fill out the gaps between the regimes you see and those you don't. Okay, that's what I wanted to say for now. Thank you very much.
Thanks, Ricardo. I actually have a few questions. I hope you don't mind if I ask. They're partly related to the question. We got 2 questions from the audience. I'm just trying to understand the model. It's really interesting. So is the idea of kind of assuming this factor model to be able to incorporate flexibility on various structures of the DAGs? So the graph could be cyclic, you could have hidden variables, you could have various interventions. So this is kind of a way to make that more flexible, right? It's like what the underlying, I guess, graph would be. Or am I understanding that?
There's actually, I was going to talk about this, but I kind of ran out of time. I mean, in fact, one way of looking at these models is the essence is condition independence between interventions and random variables, right? So you don't really care about what the possible interpretations of how these vectors come to be. So this is work. There's a lot of work by Phil David, for example, on these ideas of just boil down causal claims to this condition independence. You could have condition vulnerability here between treatment X and variable Y by just saying, well, it's just a condition-dependent statement, right, between Y and this intervention condition given X and Z. It's basically saying how X chosen is relevant, wants to know which value X took. So it's just boiled down to everything in terms of these statements. If you have directionality between X and Y, what is it? Is you have this condition dependence between Y and intervention X. That is marginal dependence between these guys. The direction here is an artifact of that, right? Because if you want to flip this edge, this will not hold. Or to treat it as a chain graph, this will not hold. Or treat it as a different type of chain graph, this will not hold. But underneath everything is just this condition dependence, and this energy-based model is as simple as it gets. If you want to have hidden variables, again, you may get to express the marginal independence constraints, which may be dense and may be useless if you have too many interactions between the signals, but that's what it is, right? But it's agnostic to whether you have cycles or hidden values and whatnot. It just boils down to that.
So it's not crucial that the interventions are on these factors. They could be on the variables themselves. That's also what I wanted to ask, because in these examples, you just need you're just hinting that the important property is that these interventions are independent of some variables in the system, right? Or
yes. So if you think about intervention single variables, be one factor for that variable that if you diverge from a particular target, then the energy goes really down, right?
Okay, yeah. So just to clarify, one short question from the audience. The interventions that you consider here, they're not necessarily binary. They're not necessarily do interventions. You're allowing for various things, right?
Yes, the meaning of these levels is completely abstract, right? You have, here I'm assuming, just for the sake of the identification results, is you have a finite set of possibilities. It could be continuous because any of these models, you could parameterize these factors as continuous functions of sigma tree. But here's just a lookup table. If you change sigma value, it's a different set of parameters, but it could be a smoother function of sigma tree.
All right. Great. Thank you for indulging my questions as well. Okay, we'll move on to the discussion now, and hopefully we'll have some time afterwards for more questions. Anish, please take the stage. Thanks, Ricardo.
Okay. Can you see my screen?
Yes.
Awesome. Yeah, thank you, Ricardo, for a wonderful talk and inviting me to be a discussant. So from my perspective, my understanding of causal DAGs and that line of work is rather lacking. So I felt the best thing I could do is try to find connections between the type of work you're doing and potentially connections with latent factor models that are quite ubiquitous in econometrics. That's where my work comes in. And so really what I was going to do is ask this big question of how to bridge intervention generalization in causal DAGs and intervention factor models with latent factor models that we study in, say, econometrics, to things like difference and differences, synthetic controls, or even recommendation systems and collaborative filtering. And so that's really what I want to get at. So I thought maybe as a way to do that, so there are two specific questions as part of that. The first one is there a way to generalize these IFMs to allow for unobserved confounding, where the unobserved confounders have a latent factorization? And the second one is there a way to map the identification conditions required for intervention generalization latent factor models to those in IFMs and vice versa? So those are the two questions I'd like to discuss. And it'll be an open discussion. I don't know the answer either. But I thought just to set that up, I'll maybe give a 2-minute primer on what latent factor models are. And then using that, we can have the language to have this discussion. If that's right, Ricardo.
Sounds great.
Okay, so what is a latent factor model? So here's a 2-minute primer. So it's normally imposed on the potential outcomes view. So say I have some potential outcome for some unit n, so it's an individual or a cell type, whatever you have, and some outcome t, so different kind of variable. And you want to know for that unit and that outcome, what is the outcome under some intervention A? The type of assumption you make in the latent factor model world is that you can write it in terms of a bilinear product of a unit-specific latent factor, which is called Vn here, and the outcome and intervention-specific latent factor, which is Wta. Okay, and it's taken as an inner product of those two things. So Vn and Wta have a low-dimensional representation, and there's some residual term epsilon and Ta. That's your source of randomness in such models. And the key thing that's being used is that lets you kind of generalize is that the unit-specific latent factor is invariant across interventions and outcomes. Okay, and that's kind of the key structural assumption, a parametric assumption that's made. And the second assumption that's made is that the epsilon nt, which is the residual term, is an independent random variable that is mean zero conditional latent factors. Okay, so that's basically the parametric assumption that's made. And the type of DAG that's fundamentally studying these things is the following, which is you have some latent factors. Those latent factors we saw, the Vns and WTAs, they can affect both the treatment assignment and the potential outcomes. Okay, and so as a result, there's confounding because latent factors affect both the assignment and the outcomes. And the potential outcomes are also a function of this additional idiosyncratic shock, epsilon and Ta. But the general assumption that's made is that the treatment assignment doesn't, it's not a function of these idiosyncratic shocks. So essentially, the confounders have some sort of low dimensional representation, okay, in some latent space. That's the fundamental assumption made in these kinds of models. And the kinds of identification conditions for generalization are as follows. They're both kind of span inclusion conditions. So the idea is that if I want to figure out what happened to some unit n under some unseen intervention A, the assumption is that the latent factor for that unit n can be written as some linear combination of some other units that received intervention A. Okay, and so that basically can write the outcome of one unit as some linear combination of the outcomes of other units that received the given intervention. And there's another inclusion, which is that if I want to learn my model, like you said, you have some observed outcomes under some intervention. Similarly here, the model, the outcomes that you learn, the intervention that you learn under, right, the WTAs you learn under that you observe, those need to be richer than the latent factors that you want to generalize to. And that's normally given as the linear algebraic condition, which is that you take the matrix of WTAs for which you have observations, that the column span of that needs to contain the column span of the latent factors for which you want to generalize. So you have kind of these two kinds of span inclusions for the unit-specific latent factor and the measurement and intervention-specific latent factor, and that's what lets you generalize. Okay, so just to go back, it's this latent factor model. It's this kind of conditional exogeneity, conditional latent factors between the assignment and outcomes, and then these two span inclusions. Okay, and so with that, I kind of want to go back to the two questions, which is that is there a way to generalize these IFMs to allow for this unobserved confounding when the unobserved confounders have some sort of latent factorization? And two, is there a way to map these identification conditions in terms of span inclusions that we have in the latent factor models to conditions you would have in IFMs and vice versa? So I have no idea what the answer is, but I thought maybe we can, all of us can have that discussion.
Right, thank you. Yes, it's a very good question, actually. Sorry?
Oh, no, I just said thank you. Please feel free to discuss, yeah.
Yeah, so what I can share my screen, just to refer to some of the slides I ever had there already. Yeah, I'm thinking about something similar to this, like what you mentioned, is which kind of alternative formulations you could have. If you look at some of the motivating processes we have here, right, like this, it's kind of a latent process between the exposure and the outcome, right? So you could think that maybe there's a sufficient dimensionality reduction approach that creates a bottleneck between these. And this will be interventions on, say, the latent distribution, and for the latent distribution, the outcomes will be invariant. To the extent you can formulate this, there's some ongoing literature on something called causal representation learning. It is kind of trying to do this, although sometimes their goals may be a bit fuzzy. I mean, I like these ideas a lot, but sometimes not very clear what is ultimately the problem they're trying to solve. So you have interventions and you have this signal that doesn't quite correspond to a one-to-one intervention. But you have images, for instance, you have exposures to a patient, but you model your raw signal as fMRI. What does it mean to say you have your stimulus causing some changes in activation? So you kind of want to extract some sort of features that have some meaning in ways they can isolate their contribution or interventions. So there's something along those lines, which again, I'm trying to learn also myself. How does it connect to, instead of using factors themselves, more in terms of these facts on the observed values themselves, more in terms of these latent components that mediate exposure to outcome.
Yeah, absolutely. Do you think there could be any particular algorithmic speed ups or benefits by somehow regularizing the unobserved confounders to kind of have a latent factorization in some way, like one would do in kind of the matrix completion literature or PCA style thing, that gives you some sort of speed up, because rather than maybe learn the densities of everything, you're saying that the densities have some sort of latent factorization that might speed up the learning process. Because you said density estimation is kind of a key bottleneck that shows up when bringing this to data.
I mean, the actual factors that you may have the moment you parameterize as a neural network, these factors themselves, even if the scope of the factor could be a large set, usually when I'm using the parameterizing data of a neural network, you may have bottlenecks in it, right? You've got the dimensionality that you have effectively is the dimensionality, the smallest hidden layer that you have in the neural network. So there's some ways of thinking about how these factors could be compressed with smaller dimensionality than the actual elements in the density. As a global compression, I don't know how easy this would be. Maybe something more along the lines of sharing some basis functions that are common to different factors and repurposing them on different factors. This might be one.
Yeah, one thing I've seen is where you kind of make the latent factors. You take your high dimensional data, you kind of learn two separate neural networks, one for, say, the unit specific latent factors, one for the intervention specific latent factors, one for the outcome specific latent factors. And then the last step of the neural network is kind of doing an inner product between those various things. And so that's one way of regularizing the fit, is that the last step of it is an inner product, like as a bilinear inner product, and the neural networks are kind of learning that latent representation that brings you to that latent factor. So it's one potential way you could regularize your neural network architecture. I've seen that works kind of effectively.
I think you have some questions coming.
I have a sort of maybe a silly question. So it looks like this kind of factor models are very general. So how is it exactly related to causal inference? It seems that you could really describe a lot of kind of structures with these factor graphs. But I guess is there some kind of modularity that's shared between the different regimes that somehow captured in these graphs?
Yes, the modularity is in the factor structure, right? If you think about the let's see, one motivator example I use was from mediation, right? If you were to have factors describing how variables respond to exposure, these factors may depend on subsets of the components of the exposure. So here the exposure is a vector of two entries. And a part of it is using one of the factors, another part of it is using another factor. And this is what the trick here would be, to be able to say, well, what would happen if I had this imaginary cigarette where there's no nicotine, where there's everything else, when my data only has smokers and non-smokers. So this is compositions about how the exposures go into factors. It's a kind of more general idea than we have with a specific graphical model. I imagine we have any factorization model, doesn't need to be up there, you go on the data network, we have an independence model that dictates a particular way of factorizing distribution. How does your action vector decompose them, these different vectors? Will tell you ways how it could be able to rearrange a new combination out of the factors that you identify.
Okay, thank you, Ricardo. I think we're just on time to finish the seminar.
Could I ask one more question? And if you need to
go for it. Then I'll finish. Yeah.
So I have a question. So I saw that you had some comments on discovery, and I am very curious. So in terms of these factor models, I guess they are. How do you think about like equivalence between these models? Like there seem to be like many different cases that could like factor models could represent such a huge class of possible models.
Yes.
Does that matter? How do you think about discovery, I guess?
Yes. So the two main tests to be solved, right? One of them is condition dependencies among the components of the model. So if we have one random variable independent of another random variable given something else, you could in principle query an oracle for that, whatever it is. The structured learning problem, of course, is you don't have, just like when you have observational data only, you only have that particular regime, you don't have the interventional regime, right? You need to be able to link what happens under one regime to another one. You need some sort of kind of faithfulness like assumptions. We have a definition of baseline as being sequences all zeros. And there you say, well, if I find this condition dependence among these random values under this design of all zeros, I will assume that this also holds under other designs. So this is kind of generalization of faithfulness to not only, it's observational to intervention procedure, right? Under the observational conditions, say independence constraint, you assume that independence constraint also hold under intervention. So here it translates into this language just means whatever discovered in sigma equals 0 will carry to sigma to another value. But there's a need to adapt to a tag, right? It needs to adapt just to the independence model of affected length. The more complicated aspect is when we have these factorizations that are not independence constraints. There's a type of interaction problem, right? So this is an interpretation. Of course, these are not random values, like sigma I and sigma j. This independency is not a usual independence. It's a kind of operational definition saying, well, if we're able to factorize these indicators on the different factors that include the data, this would simplify the model because this would break apart the interaction of the signals. It's like a novel on a graphical model space, right? Where the interactions would go. It depends how they can be distributed over factors. This is, of course, harder to test. And there are the ways or some limits of fit to test interaction, but even then, you don't have much range of variability between your factors. You won't be able to test that. But you may have ideas like what you have in hierarchical logarithm models. You have pairwise interactions that are not there. You may assume that there's no three-way interactions like we do in a hierarchical logarithm model. So these are ways where you could think, well, which other concepts of faithfulness would apply here?
Okay, thanks. I have a million more questions, but I think I can email you out. It's super interesting.
Okay, I believe that's a good time to end our seminar today. Thanks again to Ricardo for the talk and Anish for the discussion. Next week, we will have a early career event with two talks from Michael Celentano from UC Berkeley and Chris Harshall from UC Berkeley and MIT. So Michael was one of the sort of co-founders of the seminar series, and I know among all the organizers, we're very excited to see him back. So I hope I'll see you there as well. Thanks for coming to the seminar today.
Thank you.